Today's screencast is looking at Hess's law, and Hess's law is another way that we can determine the enthalpy change for a reaction. We've looked at heat of formation so far, and that's using a reference table and combining together the different heats of formation for those different substances. This is what our book calls the indirect method, and you'll find that on page 201 and 202 in your textbook. Hess's law, the book defines it as this: when reactants are converted to products, the change in enthalpy is the same whether the reaction takes place in one step or in a series of steps. So in other words, we can break it down into a bunch of different reactions that combine together to equal that single reaction that we're looking at, and we can take the net effect of those delta H's, combine those together, and that will give us the delta H for that reaction. The tricky part is finding the reactions that we're going to use and keeping in mind a couple key things. I'll talk about those in a little bit more detail in the next, when I do the sample problem. But basically, if we're going to flip the reaction, if we're going to flip the reactants and products, then we have to change the sign on the delta H. And if we multiply or divide the number of moles of reactants and products, then we have to do the same thing with the delta H value. So next I'm going to walk you through a sample problem, but it's a pretty straightforward process. So the last question on ChemQuest 78 was this challenge question. You need to add the following three reactions together to get this overall reaction. C2H4 plus H2 goes to C2H6. We want to calculate the delta H for the reaction using the delta H's of the following three reactions. Now, if you've gone through the ChemQuest already, hopefully you've learned that if we have to multiply or divide the reaction, then we have to do the same thing to the delta H. And if we have to reverse the reaction, if we have to flip it around, then we have to change the sign on the delta H. So the first thing I see when I look at these three reactions here is I see the product that I want is listed as a reactant in that third reaction. And so what I'm going to do is I'm going to take that whole reaction and I'm going to flip it around. I'm going to rewrite it down here. So it's going to be, I'll just write it right below. So 6H2O plus 4CO2 produces 7O2 and 2C2H6. Now, because I flipped the reaction around, I also have to change the sign on the delta H. And so now the sign becomes a positive 3,100 kilojoules. Now that I have the C2H6 as a product, that's a good first step. Now I'm going to evaluate the reaction to see if the reactions that are here to see if there's anything else that might be helpful. The second thing I see is I see the C2H4 listed as a reactant in my second reaction. That's good. That's what I want. And I see the H2 listed as a reactant in my first reaction, but the coefficient is a 2 instead of a 1. So what I can do here is I can divide everything by 2. And if I divide that all by 2, I also have to divide the delta H by 2. When I divide that by 2, that's a negative 286. All right, you'll notice, I'm going to change colors here. You'll notice I have my C2H4 there, that's good. I have my 1H2 here, that's good. Now in my third reaction down here, the one I flipped around, I have my C2H6, but the problem is that I've got a 2 coefficient. So I need to go back to that reaction, and I need to take this and I need to divide everything in half. When I divide that in half, I also have to do the same thing with the delta H. And so now the delta H becomes positive 1550. All right, let's clean some things up here a little bit. The 7/2 H2O will become 3.5. The 4/2 CO2 will become 2 CO2. And then the 6/2 H2O will become 3 H2O. All right, I'm going to just scribble out that third one written there so that doesn't confuse me. So now I'm going to go ahead and I'm going to look and I'm going to see if there are like terms that can be combined. And I'm also going to see if there are terms that can be canceled. For example, I see right now there's a CO2, a 2 CO2 on the product side and a 2 CO2 on the reactant side. So those two are going to cancel each other out. I see here I've got a 1 H2O and a 2 H2O, so that's 3 on the product side. And I have 3 on the reactant side here, so those will cancel out. Right? And but a lot of you are looking ahead here and you're saying, oh, right, we can combine those O2s to be 3.5 O2s. Over on the product side, I have 3.5 O2s, so those are going to cancel out. What am I left with? I'm left with the things I highlighted earlier. I've got an H2, a C2H4, and a C2H6 is my product. So I can rewrite that C2H4 plus H2 goes to C2H6. So I have my reaction. Now what I want to do is I want to evaluate my delta H's. So on the first reaction, I divided that in half, and so that's where I got the negative 286. The next reaction there, I didn't do anything with that, so it's just going to be negative 1401. And then the last reaction, I flipped it around, and so that's why I changed the sign from a negative to a positive, and then I halved it, and so that's why I did the divide by 2 to get our 1550 there. So what I'll do then is negative 286 plus negative 1404 plus 1550. Add those all up. And if we've done our calculations correctly, I'll change back to my blue here. We get a delta H, a net delta H of negative 137 kilojoules. So that then would be the delta H for the reaction as it's written here, the C2H4 plus H2 goes to C2H6. So the key is there's two things to keep in mind here. One is if we take a reaction and we reverse it, then we have to reverse the sign on the delta H. And the other one is if I divide a reaction, I have to divide every term in that reaction by the same thing, and I have to divide the heat value, the delta H, by that same thing. It would be true also if I have to multiply, like for example, maybe I needed to multiply everything here by 4. And so I'd multiply every term by 4, and I'd multiply the heat value by 4. So whatever it is you do to the reaction, you do to the delta H as well. And then we bring all those pieces together. Again, we cancel things that are on opposite sides, and we combine things that are on the same side. And the net should equal up to what we're looking for. It is kind of a process sometimes, especially if we flip. I want to talk to you a little bit today about Hess's law. Hess's law is another way that we can calculate the enthalpy change in a reaction, the delta H for a reaction. We've already learned about heat of formation. We'll also learn about how we can use calorimetry. But Hess's law is another method that we can use to figure out the enthalpy change in a reaction. Hess's law very simply states that the change in enthalpy is the same whether the reaction takes place in one step or in a series of steps. And so usually as we have it written in a problem, it's in one step, but we can actually break that down into lots of different steps if we want to. One reason why we might do this is it might be impractical to perform the reaction we're looking at in the laboratory, but we know different component reactions that make up that bigger reaction. So what you're looking at here is it's called the Ultimate Hess's Law Worksheet. It's basically a reference table, and it's got lots of different delta H's on it for different reactions, and we can piece those reactions together to figure out what the overall delta H, the overall enthalpy change for that reaction is. And so probably the best way to show this to you is to demonstrate it to you. Back here, and we look at all these different reactions that are on this Hess's Law worksheet, and sometimes it can be real tricky to figure out which one of these reactions we have to use. And so you will see the backside of the homework assignment later on this week is kind of tricky. Like, you've got to kind of dig your way through some of these reactions and see which ones are going to work best for you. You might not always pick the best route to begin with, and you might have to go back, and you might have to start all over again. And that's okay, it's part of the process. You'll see some of the problems, they give you some reactions to deal with, kind of like the example problem that we just looked at the end of Chem Quest 78. But you'll see other problems are a little bit more challenging in that you've got to figure out which one of these reactions you're going to piece together to get to the reaction that you're being asked about. And the other thing is there's a lot of variation here. So you and a friend may come up with the same answer, but use a different route. And that's okay too. It's that final end product that we're looking for, and whether you go through one reaction or whether you go through a different reaction really doesn't matter, as long as in the end it comes out to be that same reaction that you're looking for. So hopefully this is helpful for you, and you can use Hess's Law as another way to find the enthalpy change for a reaction.